Sir,
Question, sir.
Aswini sir, your voice is not audible, Aswini sir. Actually, you
Yes, sir.
started
Yes,
and
sir.
after that it was muted.
Yes, sir. Yes, sir. Now it's audible, sir.
Yeah,
Yes,
yeah, yeah.
audible, audible, Aswini sir.
Okay, okay, sir. Thank you. Thank you, sir. Thank you, sir.
एक डायलॉग आहे तुला माहित नाही.
Okay, sir. Dr. Kavati Venkateswarlu is currently working as an assistant professor, mechanical engineering department in the School of Engineering and the Built Environment JEDS campus, University of Namibia. He received his BTech in Mechanical Engineering Department and MTech in Thermal Engineering from JNTU College of Engineering, Hyderabad,
तो तुझा
and
फुल याच्यावर तुझं
PhD
समाधान झालं.
and PhD in Mechanical Engineering in IC Engines from JNTU Kakinada in 2016. He did his postdoctoral research at RAK Research and Innovation Center, American University of Ras Al Khaimah, UAE. He has 4 years of industrial experience and 23 years of teaching and research experience in the field of thermal fluids and energy. He teaches the courses related to thermal and fluids streams of both undergraduate and graduate programs of mechanical engineering. His research interests include how carbon technologies for IC engines, fuel injection strategies for supersonic combustion engines, phase change materials for thermal energy storage, hydrogen storage, and nanofluids in heat transfer and solar energy applications. He has delivered several expert talks on advanced topics of IC engines, fuel injection strategies for scramjet engines, hydrogen energy in aviation, and phase change materials for thermal energy storage in FDPs in various organizations. He has delivered two keynote sessions at national conferences held in India. Dr. Venkateswarlu has published more than 35 research papers in national and international journals of repute. He has guided 14 master's theses and guiding one master's and one doctoral thesis. He has authored two textbooks, Engineering Thermodynamics, Fundamental and Advanced Topics, and Alternative Fuels and Advanced Vehicle Technologies. He has also authored three book chapters, Low Energy and Low Carbon Buildings for Sustainable Future, Clean Energy for Sustainable Electric Power Generation, and Combined Heat and Power Generation from Hydrogen and Applications. He is a fellow of Institution of Engineers India and a life member of Combustion Institute Indian section. Dr. Venkateswarlu is also the editorial board member SAE International Journal of Engines. He is the technical reviewer for journals SAE International Journals, Journal of the Brazilian Society of Mechanical Sciences and Engineering, Institution of Engineers, and African Journal of Agricultural Research. This is the brief introduction of today's renowned resource speaker. And now I am handing over the session to Dr. K. Venkateswarlu, sir. Sir, Venkateswarlu, sir.
Yeah, yeah. Thank you very much, sir, for introducing me.
Sir,
So,
you please share the screen and you can start the session, sir. Dear participants, please mute your system. Sir, you can please start, sir.
yeah, yes, sir. I'm sharing that.
Sir, visible, sir. Hello, sir. Venkateswarlu, sir. Sir, your voice is not audible, sir. Sir, Venkateswarlu, sir.
Yes, sir. Yes, sir.
Okay, sir. Please carry
Is it
on,
okay,
sir.
sir, now? Okay.
Yes, sir. Yes, sir. Audible, sir. Please carry on, sir. Go to
Okay.
presentation mode, sir. Full
Yeah,
screen.
yes, sir. Yes. Okay, sir.
Okay, sir.
Please
Okay,
wait.
sir.
Is it okay, sir, now?
Yes, sir. Yes, sir. Please carry on, sir.
Okay. So, right. Yeah, I'm going to talk on recent advances in supersonic combustion for scramjet applications. So, I'm going to talk about the fundamental difference between the gas turbine engines and ramjet engines, then supersonic combustion and hypersonic propulsion, some challenges and the strategies for enhancing the fuel air mixing, which plays a key role in supersonic combustion. Two of the strategies like intrusive as well as non-intrusive flame holding and injection strategies. And then strut injection with a focus in scramjet applications. And I'm going to talk about strut in combination with other injection strategies. And then strut injector cooling, which is one of the major challenges associated with the strut injection in supersonic combustion in scramjet engines. Then blunting of the leading edge of the strut. Then some studies on this in this field. Okay, so as far as jet propulsion is concerned, the turbofan engine is the most widely used powertrain for powering the commercial aircraft. And of course, turbofan or turbojet, which are equipped with afterburner, are the powertrains in powering the military aircraft. But in addition to this, turbofan or turbojet with afterburner, the ramjet is another type of air-breathing jet engine, which is used to power the military aircraft or missiles. So there is a fundamental difference between gas turbine engines and ramjet engines. So whereas in gas turbine engines, there is a compressor which is used to compress the incoming air before it's entering into the combustion chamber. And of course, the compressor is run by the turbine. But whereas in case of ramjet engines, there's no compressor and hence there is no turbine. As of course, the net power output of the turbojet engine is basically zero, right? So the purpose of turbine is to run the compressor as well as some other auxiliary parts. So the network output of the gas turbine cycle is zero. So here in ramjet engines, there's no compressor, but instead the ramjet compresses the incoming air with the high-speed vehicle. So it also makes use of some kind of shock cones to decelerate the flow of air which is entering into the combustion chamber, so that the air enters the combustion chamber at subsonic conditions. So that means the combustion is subsonic, be it gas turbine engine or ramjet engine. But in case of supersonic combustion ramjet, scramjet engine, as the name indicates, the combustion is at supersonic conditions. So the flow is not decelerated. So that means the flow will be continued supersonic velocities throughout the combustion chamber. So that is the reason it is called as supersonic combustion ramjet engine or scramjet engine. So it is a variant of what is called as ramjet engine. So here we can see that an afterburner equipped with the turbojet engine equipped with an afterburner. So we can see here, this is the afterburner, which is located between the turbine and exhaust nozzle. Okay, so whenever there is an extra power needed, this afterburner, the fuel is directly injected into this afterburner, so that this increased energy provides more thrust. So for short takeoffs or combat conditions, this afterburner, so this jet engine with afterburner is typically used in military aircraft for short takeoffs as well as for combat conditions. So this is a modified version of turbojet or turbofan engine equipped with an afterburner for more thrust requirements. And this is a ramjet engine. So as I said, there's no compressor. So but incoming air is basically compressed with the ram effect. So high-speed aircraft compresses the incoming air, but however the air velocity is decelerated before its entry to the combustion chamber. So that means the combustion takes place at subsonic conditions, just like gas turbine engines. So there is an isolator in between the intake as well as combustion chamber. So the purpose is to act as a basically a buffer. It acts as a buffer, and it makes use of a shock train to prevent any high pressure gases to cause boundary layer separation, which is one of the important issues in case of supersonic combustion, right? So that means this isolator basically reduces the tendency of boundary layer separation by making use of a shock train. So this is the structure of a ramjet. So of course, nozzle is used at the exit, which will accelerate the fluid to the supersonic velocities in case of this ramjet engine, because the combustion is at supersonic. So the nozzle accelerates the fluid to the supersonic velocities, so that the ramjet can be operated at a Mach number range of 3 to 6. So the inlet structure is in such a way that it compresses as well as decelerates the fluid so that the air enters at subsonic conditions. So that means air is basically reduced to a subsonic velocity of around Mach number 0.2. But however, the propulsion is maybe supersonic. So that's the reason ramjet can operate within the Mach number range of 3 to 6. Yeah, this is a variant of scramjet engine. It's a modified ramjet engine, which is scramjet or supersonic combustion ramjet. So it also relies on the same principle that incoming air is basically compressed by ram effect. But however, here there is no deceleration of the flow, but instead the flow is continued supersonic. So that is the reason the air enters into the combustion chamber at supersonic conditions. So that is the reason it is possible to accelerate the fluid or exhaust gases to the hypersonic velocities above Mach number 6. So this is the main feature of this scramjet engine, so which is a variant of ramjet engine. So it also doesn't have a compressor and of course the turbine. So this is a typical supersonic flow. So we can see here a gas, basically the jet, a rounded jet is injected into the supersonic cross flow. So there is a bow shock which is formed ahead of this jet. And of course, there is an inverse pressure gradient which is developed, so which will basically create some kind of mixed zone, okay, recirculation zone, so that there is also some boundary layer separation. So which is of course somewhat required, but increased pressures or whatever they will basically increase the pressure loss, and of course reduce the mixing efficiency or whatever it is. So that means the shock waves are typically used in both ramjet as well as scramjet to create some kind of recirculation zones in order to allow for efficient mixing of the fuel and air in ramjet as well as in scramjet. The only difference between them, those two, is whereas in the ramjet the flow is decelerated, but whereas in scramjet the flow is continued to be supersonic before it's entered into the combustion chamber. So that means the flow continues to be supersonic in scramjet engines. So we can see here there is a breakup of the fuel. So and then atomization. So because the fuel has to be broken down to the small particles, then they have to be atomized so that the fuel can mix with the air effectively. So this is the typical flow of mixture, right? So fuel air mixture in the supersonic combustion. So actually there are different variants in ramjet. So ejector ramjet and turbojet ramjet mode, and of course there are different variants which are used in combined cycle engines like rocket based combined cycle or turbine based combined cycle or in other combined cycles. So the main advantage in this combined cycle is, for example, if you take rocket based combined cycle, so it combines the advantage of rocket, that is high thrust to weight ratio, and then a high specific impulse of jet engine. So basically jet engine is known for its high specific thrust, whereas this rocket is high power, high thrust to weight ratio. So this gas turbine engine is known for its high specific impulse, that is specific impulse. So that is this. There are different variants from ram to scram. So that is these are the different variants: ejector ramjet, turbojet ramjet, or ramjet scramjet. So ramjet to scramjet transition or whatever it is. So this is a typical, this is a ramjet powered Talos missile, which was developed by USA in 1950s. So for its military operations. So the main advantage of this ramjet or scramjet is basically the light structure. Okay, mainly as it doesn't have, they don't have any moving parts like the compressor or turbine. So the structure is basically light, and moreover. So that the acceleration can be made hypersonic, supersonic, or hypersonic, depending on the variant. So if it is a ramjet, supersonic velocities at exit, or if it is scramjet, it can be possible above 6 Mach number or hypersonic conditions. So that means both use high velocity or high speed of aircraft to compress the air. So that means they require a boost device to bring them to the initial speed required for compression or whatever. So that means they require a boost vehicle, maybe a rocket or other boost vehicle to bring them to the desired speed, required speed before they compress the incoming air. So, but anyhow, the main advantage is they are light in structure, so that they can accelerate the fluid for the supersonic as well as hypersonic. So the hypersonic propulsion is possible with this kind of scramjet engines, and supersonic propulsion is possible with this ramjet engine. So the scramjet basically operates between within a Mach number range of 5 to 14. So that is they can operate at hypersonic conditions, so above Mach number 5. So that is the main advantage. That is the reason it is the future engine for all missiles or powering military aircraft. So yeah, this is the operating range of ramjet as well as scramjet. We can see that the ramjet is effective between within the Mach number range of 3 to 6, whereas scramjet is effective above Mach number 6. That means it is suitable for hypersonic propulsion systems, whereas ramjet is suitable for supersonic flights, supersonic flights. Okay. Yeah, if you compare both ramjet as well as scramjet for different Mach numbers, so we can see here the scramjet Mach number is high when compared to that of ramjet. So that means here we can see that the scramjet can attain above Mach number at a combustor length of around 1.7. We can see that around after 1.7, the scramjet can attain a Mach number of more than 1. So that means supersonic combustion is possible at a combustor length of around 1.7. So the scramjet maintains higher Mach number throughout the combustion chamber, but however at exit nozzle, the ramjet Mach number is something higher. So that means the scramjet maintains higher Mach numbers when compared to that of ramjet during the combustion. So, and if we compare the total inlet temperature of both ramjet as well as scramjet, yeah, we can see that the ramjet inlet temperature is higher when compared to that of scramjet counterpart. Yeah, it's mainly it's due to the conversion of enthalpy to the conversion of kinetic energy to the enthalpy, so which will raise the temperature. So here, basically the flow is decelerated to subsonic velocities of around Mach number 0.2. So because of that, the conversion of kinetic energy into enthalpy, there is a rise in the pressure as well as temperature. But whereas in the scramjet engine, the flow is not decelerated. So because of that, the combustion, the total inlet temperature is less in case of scramjet engine. So this is the advantage with the scramjet engine, since it allows for, since it maintains the total inlet temperature under control. So it is possible to accelerate the exhaust gases to very high velocities, hypersonic velocities. So this is the comparison of total inlet temperature. So which is more in case of ramjet when compared to that of scramjet. So because of fully conversion of or maximum conversion of kinetic energy into enthalpy, then because of that there is a rise in the pressure as well as temperature. And this is the total pressure in both ramjet as well as scramjet. But here we can see that the total pressure loss is more in case of ramjet when compared to that of scramjet. That is the reason the total pressure is also less in ramjet when compared to that of scramjet engine. So here the combustion efficiency, if you compare them, the ramjet has more combustion efficiency when compared to that of. It can be correlated to the higher inlet temperature of the ramjet. Okay, so that is the reason the combustion efficiency is also higher in case of ramjet during the okay, and along the combustion chamber length. So we can see that, and these are the number of publications from. So we can, if we compare that from almost 2000 onwards, there is a rise in the supersonic combustion research. Okay, when compared to that of subsonic combustion, there is a surge in case of supersonic combustion research. As we can see nowadays, there is more widespread interest in case of supersonic combustion when compared to that of subsonic combustion, especially for military or missile propulsion systems. Yeah, there are actually the hypersonic propulsion systems are basically operated by either liquid operated or solid propellant rockets mainly. Then ramjets, ducted rockets or scramjets, and dual combustion ramjet. So all these are basically hypersonic propulsion systems. So we know that the rocket boosters are used to propel hypersonic vehicles for mainly for space applications, to launch a space vehicle, or for rockets are also used for powering the long range ballistic missiles or whatever it is. So then there is more research interest in case of scramjet engines for military applications. So for hypersonic vehicles. Okay, so that is the reason the more research is going on scramjet engine to develop and for hypersonic propulsion systems, especially for missiles, operation or military aircraft purposes. Yeah, when you but however, there are certain challenges to design a hypersonic propulsion system which are capable of running at orbital velocity. So mainly when you consider the high Mach numbers, okay, when the speed increases, there is basically the rise in total temperature or stagnation temperature. So it makes the design somewhat difficult, because the materials that can withstand this high stagnation temperature or the total temperature. So there is basically the problem is the materials. Okay, the materials which can withstand these high temperatures, we have to choose some advanced materials. Okay, so that is one of the challenging tasks. Then maintaining combustion stability at hypersonic speeds. So basically the combustion. Yeah, we have to continue. We have to maintain the combustion stability during a wide range of Mach numbers. So in order to design a hypersonic vehicle, so the combustion has to be stabilized, because there is mainly the residence time for fuel air mixing is quite less in case of supersonic combustion, especially the scramjet engines. The residence time is quite low, which is some milliseconds. So during this short period of time, it's very difficult for fuel to mix with air. So that is the reason the combustion stability is also dependent on this injection. Then of course flame holding things. So that means the combustion stability is one of the challenges associated with the supersonic combustion or hypersonic propulsion systems. And then other difficulties involve the fuel that is chosen. Mainly, the fuel should act as a regenerative coolant so that it can take some heat which is liberated in the combustion chamber. So that means if we have to choose the fuels in such a way that they can act as a regenerative coolants to take the heat that is generated. And then the weight and efficiency are other important factors. Okay, so thrust to weight ratio is important for supersonic or hypersonic vehicles. So especially rockets have a high thrust to weight ratio. So then another important thing is transitioning to rocket propulsion, because the ramjet or scramjet, as they use vehicle speed, high speed of the vehicle to compress the incoming air, they require some kind of boost devices. So that means the transitioning to the rocket propulsion is another difficult tasks. So these are the different challenges which have been which are considered for research. And of course, there is more research and more interest for the scramjet engines and the design of supersonic as well as hypersonic propulsion systems. So if you consider the fuel and engine options as a function of Mach number, so we can see that okay, this is the comparison of the fuel as well as engine options as a function of Mach number. Okay, we can see that this okay, the turbojet engines are basically effective between up to Mach number of 3, whereas ramjets are effective between Mach number of 3 to 6. And then the scramjet is effective above Mach number 5 up to Mach number 14.
Sir, Venkateswarlu, sir.
Yes, sir.
Sorry to disturb you, sir. Sir, your voice is a little bit low, sir.
Okay, sir. So is it okay, sir, now?
A little bit.
Okay, so if you compare the fuel as well as engine
okay,
options as a function of
Carry
Mach
on, sir.
number, we can see that the turbojet engines are basically effective up to a Mach number of 3. So whereas the ramjet is effective within a Mach number range of 3 to 6, and scramjet is effective above 5 up to 14 Mach number range. And rockets are, of course, they're better at higher Mach numbers, around 25 Mach number. And if we consider the fuel options as a function of Mach number, we can see that the hydrocarbon fuels are effective up to Mach number of 8. But whereas the hydrogen is a better choice or a better candidate as a fuel at a wide range of Mach numbers. So this is due to the fact that hydrocarbons basically are not suitable at high Mach numbers. So there are certain drawbacks associated with this. We will discuss that later. Anyhow, so that means hydrocarbon fuels are effective. So we can use the hydrocarbon fuels like kerosene or other jet fuel, jet A, jet P, or whatever it is. They are effective up to Mach number of 8. But to cover wide range of Mach numbers, hydrogen-like fuels are essentially required. So, hydrocarbon fuels basically due to certain the silent features like their energy density is high. So that means if you consider the jet fuels, their high energy density is one of the important features which will allow them as a jet fuel, so that they can provide a long range operation. So that means their energy density, so the energy stored per unit volume is quite high when compared to the fuels like hydrogen, which has a low energy density, or volumetric density of hydrogen is quite low. So which necessitates the high storage, large storage tank. But however, in case of this hydrocarbon fuels, their high energy density is high, so that they can they can allow long range operations. And in addition to that, the availability is also wide, and also they can be stored easily. So because of these reasons, they are considered as the fuel option for aerospace applications. But however, after some Mach number of 8, so if you go beyond the Mach number 8, there are certain challenges associated with these hydrocarbon fuels, mainly thermal management constraints. So as mentioned earlier, so with increase in Mach number, obviously the total inlet temperature will be more, so which poses challenge, so that the regenerative cooling fuels are necessarily required. So that means hydrocarbon fuels fail to absorb this heat when the Mach number increases over 8. And also, insufficient net thrust is another drawback. So that is actually, in case of high Mach numbers, the enthalpy of incoming air becomes more, so which becomes high, which is almost comparable to that of heat released in the combustion chamber. So because of that, what happens is that the heat release rate will be reduced. So that means at high Mach numbers, the incoming air enthalpy is more, which is almost equal to that of heat release rate. So that means heat release rate will be reduced because of this high enthalpy incoming air. So obviously, the thrust generated is adversely affected because of this reduced heat release rate. So because heat release rate plays an important role in uh, combustion chamber. Okay, so then poor mixing in combustion. So basically, if you consider the jet fuel, maybe kerosene, so it is the ignition. So ignition timing is higher. So because ignition is longer. So that is the reason the mixing is not effective. So that means the kerosene cannot easily mix with the air, as in the supersonic combustion, the time available is very less. So the effective mixing of the fuel and air is almost not possible with at higher Mach numbers. And another important drawback with this hydrocarbon fuels is thermal instability. So because at high Mach numbers, there is a tendency of hydrocarbon fuels to break, so that they can form some deposits. So this is another important drawback, so that they cause thermal instability. So because of these drawbacks, at high Mach numbers, the use of hydrocarbon fuels is not recommended. And if you compare the fuel properties of hydrogen and with the other jet fuel, we can see that the hydrogen basically has a wider flammability limit. So because of that, it can allow for efficient, easy ignition. So that is one of the important advantages with this hydrogen fuel and compared to the jet fuel. And moreover, its heat of combustion is also higher, almost 2.8, 2.9 times higher than that of jet fuel. But however, its volumetric energy density is quite low when compared to that of other jet fuels, so necessitating the large storage tank. So that means the long range operation is not possible with this hydrogen fuel, as its energy density, volumetric energy density is quite low when compared to the jet fuels. Despite its wider flammability limits and heat of combustion and other important properties, its volumetric energy density is quite low, so which necessitates a large storage volume tank. So this is another important drawback associated with this. And also, the gaseous hydrogen like fuels storage as well as handling is also something difficult. Okay, so this is the propulsion performance comparison of various jet engines, and then the fuels like hydrocarbon as well as hydrogen. Yeah, if you compare the jet engines and the rocket engine, we can see that the specific impulse, which is the fuel efficiency. Of course, specific impulse is basically the fuel efficiency. It's a measure of fuel efficiency. So we can see that the turbojet engines, turbofan or turbofan with afterburner, their specific impulse is high at low Mach numbers. So that means with increase in Mach number beyond 3, their specific impulse decreases. So that means their efficiency goes down with increase in the Mach number. Then the ramjet is effective between 3 to 6 Mach numbers. So that means so it can be operated effectively between Mach number range of 3 to 6, and then scramjet can be operated above 5, 6 or Mach number up to 14. But rocket has, of course, rocket is known for its high thrust to weight ratio, but its specific impulse is almost constant during all the Mach numbers considered here. But and when you compare the fuels, the hydrogen, this is liquid hydrogen and hydrocarbon fuels. So the hydrogen has no competitor at all as a fuel, as we can see that its specific impulse is higher at high Mach numbers. But whereas this is the curve for hydrocarbon fuels. So that means there's no comparison at all between the liquid hydrogen and hydrocarbon fuels when you compare the specific impulse versus Mach number range 0 to 10. So these are the flight demonstration tests of the scramjet engine to power missiles, military aircraft. So the first hypersonic aircraft was tested by United States in 2004. That is X-43A hypersonic aircraft. So which was powered by scramjet engine with hydrogen fuel. But though earlier attempts by United States in combination with Australia, joint venture of Australia and United States in 2002, it failed. But anyhow, this is the the first hypersonic aircraft powered by supersonic hypersonic aircraft powered by scramjet engine powered by hydrogen. But however, the Russia in 1991 tried that is for powering missiles. Okay, so a missile powered by the scramjet engine. So that means that the first hypersonic aircraft was tested by United States in 2004, which was powered by scramjet engine with hydrogen fuel. Yeah, this is the NASA's X-43 hypersonic aircraft powered by scramjet engine, which was tested in 2004. And then when you consider the challenges in supersonic combustion, the main okay, if you consider the challenges in supersonic combustion, yeah, basically the fuel air precedence time is quite low, which is of the order of some milliseconds. That is one of the important challenges to design a supersonic combustor. And of course, the liquid kerosene is the mainly one of the, it's predominantly used as a fuel for the jet propulsion engines, okay, because of its wall cooling effect. But however, when you compare the kerosene with other gaseous fuels, its ignition delay is longer. Ignition time is longer. So that means it requires longer time for breaking up of the fuel as well as atomization. Okay, breaking, atomization, and mixing with air. So it takes longer time for all this process. So breaking and then atomization and mixing with the fuel, air, it takes longer time because of its longer ignition delay. So it is one of the important drawbacks of this kerosene fuel. So another important challenge is the shock waves and the boundary layer interaction, which will cause some kind of pressure gradients or pressure losses. So thermal losses, thermal loads, which will increase the thermal loads. Okay, so shock wave interaction, that means shock wave and boundary layer interaction is another important challenge, which is in the supersonic combustion. Then the flame stabilization is another important challenge, as the duration for fuel air mixing is quite low. So we need specialized injectors like maybe strut or cavity or whatever it is. So yeah, it is another important challenge. So these are the important challenges associated with the supersonic combustion. So this is the typical parallel fuel injection in case of scramjet engines. So we can see that the fuel as well as air flow in the parallel directions. But however, with this parallel injection, we know that the mixing is not that effective in the parallel injection. And in the this is a normal injection where the fuel is injected in the normal direction to the air flow, but there is a bow shock which is formed ahead of this okay, the fuel injection. Okay, so which will create some kind of boundary layer separation. So fuel air mixing is something disturbed with this kind of boundary layer separation when the fuel is injected normally to the airflow. But however, it is the mixing is something effective when compared to that of parallel injection. So to address the issue of ignition delay of kerosene, there are certain strategies which were used by some researchers. One is laser induced plasma ignition. So which makes use of some a focused laser to generate a high temperature plasma. So, so that means a high temperature plasma kernel is generated by this induced plasma. So that the fuel is ignited. So the kerosene fuel is ignited with this laser induced plasma ignition, which makes use of a focused plasma, laser plasma. Okay, so the another technique is the pilot hydrogen injection. So hydrogen is used as a pilot fuel to ignite the mixture. So ignite the fuel. So that means the hydrogen is basically injected as a pilot fuel before the main fuel is injected. So once the ignition is started, the fuel is injected, remaining fuel is injected into the combustion chamber. And another technique is air throttling, which is basically spraying air so that it will reduce the airflow velocity. So this is actually injecting the secondary air into the combustion chamber so that it will reduce the airflow. So it will increase the back pressure so that the ignition is possible with this air throttling. So these are the three important techniques which have been used by researchers to address the issue of ignition delay of kerosene in the uh, jet propulsion engines. So, in order to address the issue of the fuel air mixing, as the fuel air mixing time is quite low in case of scramjet engines, it is in order of the milliseconds. So, in order to enhance the fuel air mixing process in scramjet engines, there are two main techniques which have been developed by the researchers. One is intrusive technique, other one is non-intrusive technique. So, in the intrusive method, basically the fuel is injected from an obstruction. Maybe strut, ramp, or pylon are used as an obstruction. So this strut or ramp, these are basically placed in the supersonic flow. In the core of the flow, they are located so that they can create some obstruction for fuel and air flow, so that the fuel air mixing is effective with this obstruction type of fuel injection, right? So strut, ramp, or pylon are the intrusive method of injection techniques. And then another important method is non-intrusive method, which basically there are the two types of non-intrusive techniques. One is flush wall injection, other one is cavity-based injection. So the flush wall injection, basically there are some ports or holes are created in the walls of the combustion chamber. So the fuel is injected directly into these ports or holes in the combustion chamber walls. So with this wall injection, the cooling effect is achieved with this. And then another technique is cavity-based injection, which also comes under the category of non-intrusive technique. So here, some kind of cavities are created in the wall of the combustion chamber. So the fuel is injected into this cavity region. So that is called as cavity-based injection. So that means this wall or cavity-based injection come under the category of non-intrusive method of injection, whereas ramp, strut come under the category of intrusive technique. So here, in the non-intrusive method, actually the fuel is injected directly from the combustion wall or wall-mounted cavity with direct injection in the cavities, or a combination of these two methods. So that is in the non-intrusive method, so the fuel, flame holding is basically achieved with this direct injection or wall-mounted cavity, or combination of these two techniques. So this is an intrusive method. So actually there are struts. So we can see that strut so there are two struts. Okay, so strut-based injection strategy, which is an intrusive method of injection. So strut basically creates some kind of obstruction in the fluid flow. We can see that so air. This is the supersonic airflow. So air enters with a supersonic velocity above Mach number 1. So here when the struts are placed in the combustion chamber, in the core of the flow, they create some kind of obstruction so that some kind of shock waves are generated. So because of that, the fuel air mixing is effective So with this kind of strut injection strategy. So this is a strut plus wall injection strategy. So here we can see a strut is located in the combustion chamber, core of the flow. So here the air enters at a Mach number of 3 here. And these are the wall injections. So there are slots in the walls of the combustion chamber. There are 2 slots. So where the fuel is injected again. So that means the fuel injection is affected into the struts as well as into the slots made in the walls of the combustion chamber. So this is strut plus wall injection strategy. So that means a combination of strut with other injection like wall injection. So this is a non-intrusive method of injection. We can see that the fuel is injected. This is vertical wall injection, but here angled injection. So transverse injection where the fuel is injected at an angle. Uh, so these 2 types of wall injection are the non-intrusive method of injections. Yeah, this is another the cavity. So this cavity-based injection. We can see here single cavity and this tandem or series cavities. Two cavities are located in series, and here the 2 cavities are located in parallel direction. So this is single cavity. This is tandem cavity or series cavity and parallel cavity here. So when compared to that single cavity, so the multi cavities, maybe series or parallel, they increase the fuel air mixing somewhat. So fuel air mixing is better in case of either series or parallel type of cavities. But however, when compared to this series, parallel cavities increase the heat transfer rate, because we can see that the injectors in opposite direction can create. Okay, there is okay. This is the recirculation zone which is formed in the around the cavities. So because of this, the heat release is centered, and of course, the effective heat release rate is possible with this parallel cavities when compared to this series cavities. But here in the series cavities, though the mixing is effective, the pressure loss is somewhat higher when compared to that of this parallel cavities. But however, there are advantages with each of these methods. So then when you compare the strut with other and strut and cavity, so which are the 2 important uh, flame flame molding techniques, or fuel injector or flame molding techniques. So these are the 2 widely used techniques, strut as well as cavity. So when you compare these 2 strut as well as cavity injection schemes, we can see that the strut basically allows more deeper penetration of the fuel and air, because as the strut is basically located in the core of the flow, the fuel air mixing is okay. There is a deeper penetration of the air into the fuel. Okay, so because of this, effective mixing is possible. But however, in cavity case, the fuel will not reach the core of the flow, as the fuel is injected into the cavity, which is located in the walls of the combustion chamber. So that means when the fuel is injected into these cavities located in the walls of the combustor, so the effective mixing is that means the fuel will not reach the core of the flow. That is one of the drawbacks of this. But however, when you compare other parameters, both this strut as well as cavity, we can see that uh, in case of strut, actually the mixing efficiency is better when compared to the cavity case. But however, the strut also promotes some kind of okay, physical choking, and of course, in case of multi strut injection, there is just flow stagnation at the leading edge of the struts, as when you use more than one or two, more than one strut. So multi-strut case, there's a flow accumulation or stagnation at the leading edge of the struts, which will lead to some kind of thermal choking, and of course thermal protection problems will arise. So that means when a strut is basically used for effective mixing, but however the physical choking and pressure loss are more in case of struts when compared to that of that means these when you compare these 2 injection schemes, they have advantages as well as disadvantages. So yeah, the strut as well as cavity are the 2 widely used fuel injector or flame holding techniques as far as the scramjet injection engines are concerned. So Yeah, yeah. The main the purpose of this strut is to allow failure mixing because of reduced residence time. Strut creates an obstruction. So because of that, there is more scope for fuel and air mixing. So that means they create some kind of low speed zones so that the fuel air residence time can be something increased. So then actually there are different strut configurations, diamond strut, wedge strut, wavy strut, and trapezoidal or rectangular or grooved struts. So out of these, actually, the diamond and wedge struts are most widely used struts in a scramjet combustor. Yeah, this is actually a diamond strut, and this is the wedge strut. So when you compare these two struts, actually, which are most widely used strut configurations, the diamond as well as wedge struts. So actually, in case of wedge strut, the mixing is better in case of wedge struts when compared to that of diamond struts. Yeah, this is actually another type of lobed strut. This is another type of strut, and these are the grooved struts. Yeah, this is actually the DLR combustor, scramjet combustor, which is the basis for research on scramjet combustor. So DLR combustor, which is a German aerospace research center's no, the design. So this is the basis for all the scramjet research. So basically, the strut length is 32 mm, and of course the high here the angle is half angle is 6 degrees. So and again there is actually the combustor diverges at an angle of 3 degrees to allow for some kind of boundary layer to reduce the boundary layer separation or whatever. So here the combustor the upstream combustor diverges at around 3 degrees angle, and we can see here the strut length is 32 mm. So the combustion length is around 300 mm here. So the air can be supersonic. Okay, air enters at supersonic conditions, maybe above 1, 2, or 3, or whatever it is. So when you compare the combustion efficiency and mixing efficiency of the two strut or single strut, you can see that in case of two strut injector, the mixing as well as combustion efficiency are higher. But however, it is accompanied by increased total pressure loss in case of multi-strut or two-strut injector. So that means when there is an increase in the combustion or mixing efficiency, they are accompanied by the total pressure loss in multi-strut injectors, strut injectors. So the multi-strut injectors, the main drawback is at the flow accumulation or flow stagnation at the leading edge of the struts, which will cause some kind of thermal choking, leading to thermal management problems. So this is the main drawback of multi-strut injectors. So in order to overcome these drawbacks of the struts, the strut in combination with the cavity or strut ramp in strut or strut with wall injection techniques are also in use to mainly overcome the drawbacks of strut, multi-strut or whatever it is. So here it's a strut in so there are cavities actually. This is a strut only injector. Here a strut, a strut with cavities. So we can see here the cavity is located at a length of 110 mm from the leading edge of the combustor. And in the third case, it is the cavity is located at 120 mm from the leading edge of the combustor. So that means this is the strut only configuration, but here strut with cavities. Two cavities located upper as well as lower wall of the combustor. But in the third case, okay, in second and third cases, the cavity is located at 110, and in third case 120 mm from the leading edge of the combustion chamber. Yeah, we can see that in the case 1, case 2, case 3. So the strut only and the strut with two cavities at 110 mm and cavities with 120 mm. So we can see that so that means the case 2 and 3, the duration of the combustor, okay, the combustor length is reduced. That means the fuel H2 and H2O are fully absorbed when in case of this strut with cavity. So that means strut only configuration requires more combustor length when compared to that of strut with cavity. Okay, that means the third configuration is effective. So that means it requires less time for complete mixing. Okay, so we can see that here. So this is the case 1. So we can see case 1, case 2, case 3. So that means case 3 requires less duration for mixing, complete mixing. But here at the 200 we can see that only case 3, sorry, case 1 is only remaining here. So that means H2, this is the mass fraction of H2 absorbed, and this is the mass fraction of H2 absorbed. So if you compare that, the case 3 is effective. That means it requires less duration for complete mixing and compared to the case 2 and compared to case 1 as well. So that means this strut only configuration requires more combustor length for effective mixing. So that means combustor length can be reduced. So because of this strut with cavity, that is the advantage with this strut in cavity, right? So here, if you compare the mixing efficiency as well as combustion efficiency, also we can see that the combustion efficiency in case 3 is higher when compared to that of case 2 as well as case 1. So combustion has, so when the mixing efficiency is higher, obviously the combustion efficiency is also higher in case 3 when compared to other two configurations. So this is a typical ramp in strut. Okay, there are 2 ramps in strut. So this is another configuration to overcome the drawbacks of strut. So this is another important so strut plus wall injection. So where there are, see, we can see here wall injection here, hydrogen is injected into the walls here, and there are 2 struts, 3 struts as well. So multi-strut and wall injection strategy this is. So that means hydrogen is injected into the walls as well as into the struts here, into the airflow. So then the strut, okay, because of the strut, when it is located in the core of the combustion chamber, core of the flow, the strut is basically surrounded by high enthalpy incoming gases. So because of that, there is a problem of overheating of the strut. So automatically, when the cooling effect is not provided, so there is a possibility of strut damage and of course engine damage. So especially at high Mach numbers, so when the total inlet temperature becomes 2700 Kelvin, whereas the post combustion, I mean exhaust gas temperature can reach as high as 3000 Kelvin at higher Mach numbers. So at this high Mach numbers, again the heat flux will be around 10 megawatts per meter square, so that it creates some problems like thermal protection. So unless the strut is cooled properly, so there is a possibility of strut damage. So strut cooling is essentially required since it is located in the core of the combustor. So actually there are 2 different cooling techniques. So passive as well as active cooling methods. So the passive methods adapt some kind of high temperature alloys, super alloys or composites, so which are used in rockets as well as air breathing jet engines. So then another this is actually Ta10W. This is actually titanium tungsten alloy, which is also most promising in high temperature environments. And another is passive technique is basically carbon or carbon silicon carbide composite in high temperature environments, so which are used in rockets as well as scramjet engines. So these are the passive method of cooling techniques. And another one is active regenerative cooling, which typically uses the onboard fuel, maybe hydrogen or kerosene or whatever. So an onboard fuel is basically used as a coolant, which is actually circulated uh, through the channels provided around the strut. So in order to achieve the cooling effect to the strut, this active regenerative cooling by making use of the onboard fuel, so which is injected through the channels. This is another technique which is active cooling. But however, yeah, there are certain drawbacks with this, challenges with this active regenerative cooling, because so because this high temperature environment also promotes some kind of oxidative as well as pyrolytic coking, so that the hydrocarbon fuels, there is a tendency of breaking down at these high temperatures, high temperature environments, so causing some deposits or whatever. So that is another important challenge for this strut cooling. So this is the regenerative cooling of the scramjet engines. So you see here, this is the coolant is circulated here. This is the combustion gas flow and the coolant flow here. So here actually the heat transfer will be from combustion gases to the walls by convection, and then in the walls it is by conduction, again by convection from the walls to the coolant. So this is a regenerative type cooling of scramjets. And another is actually transpiration cooling or film cooling of the scramjets. So it is actually the coolant is basically circulated through the porous medium, so that it is the main advantage with this is it is possible to cool, okay, with the help of sensible cooling as well as phase change cooling. Okay, so that means it is transpiration cooling of scramjets, which makes use of which is basically spraying the fuel, okay, coolant, spraying the coolant, maybe in water or nitrogen or whatever it is, through the porous medium, right? So that sensible cooling as well as phase change cooling takes place here. So because of that, the effective cooling is possible with this. And then another important technique is actually blunting of the leading edge of the struts. So in order to reduce the heat load on the strut, so the blunting of the leading edge of the strut is the effective application. Okay, so it will reduce the heat load on the, that is by cutting a part of the strut at the leading edge. Okay, so strut can be okay by cutting and removing a part of this strut at the leading edge, so that it can be made as a sharp corner, right? So we can see here, this is the strut, basic strut, and this is the blunted one. So because of this blunting, the strut length is reduced. So we can see here, this is of course 2 mm. So here we can see here again, so strut length is reduced actually. So that means by cutting and removing a portion of the strut at the leading edge, so the thermal load will be reduced. So that means it takes the heat. So because of that, thermal load and the strut will be reduced. So this is called as blunting of the leading edge of the strut. So, but actually, the strut can of course reduce the heat load. Okay, blunting can reduce the heat load, but however, there are the problems like, of course, it will reduce the mixing efficiency, and also it will increase the total pressure loss. So blunting can maybe it will reduce the mixing efficiency as well as total pressure loss, but however, it will provide the cooling effect to the struts. Yeah, this is actually configuration we can see here. The strut can be cutting a portion at the leading edge and removing that. So we can see here, this is actually a strut with sharp edge, and this is the blunted edge. Okay, so 10 mm. Okay, this is actually 10 mm. Another one 20 mm cut. Okay, so here we can see that this is the sharp edge blunt. So blunt, the strut without blunting, and here a strut with 10 mm blunting, and this is strut with 20 mm. So we can see here a sharp edge, sharp strut will obviously provide some kind of recirculation zones. So that is the shock wave is, the strength of the shock wave is okay, it is better here. So because of that, the effective mixing is possible. That means when you blunt the strut leading edge, a part of that, obviously what happens is the shock strength is reduced. So we can see here. So the shock strength is reduced here with the okay, so here it is more effective when compared to these two cases. Okay, so that means shock strength is reduced when you blunt it. So because of that, what happens is the mixing effectiveness is reduced with this blunting of the leading edge of the struts. So we can see here wedge strut. Okay, in case of wedge strut and blunted wedge, okay, 10 mm, 20 mm, and then rounded, okay, 10 mm rounded like that. So we can see here the mixing efficiency is higher for wedge only strut. So without blunting, but the mixing efficiency decreases with blunting. Okay, again the total pressure loss also more for blunted one in case of okay, when compared to that of wedge struts. So as part of so my research, I'm focusing on blunting of the leading edge of the strut. For that, I considered two wedge as well as diamond struts by blunting at the leading edge, so that the radius will be 5 mm. So we can see here, these are the two strut configurations. So this is the wedge strut, and this is blunted wedge, and this is diamond strut and blunted diamond. So these are the strut configurations so that I and my co-researcher are working on this. So we are actually working on different Mach numbers, 2, 2.5, and 3. So with these four configurations, okay, one is uh, wedge strut and blunted wedge, diamond strut, and blunted diamond strut. So these are the streamlines for three cases. Okay, sorry, three different Mach numbers. So Mach number 2, 2.5, 3. So this is for wedge strut. This is for wedge strut at different Mach numbers, and this is for so wedge strut with the blunted edge at the same different Mach numbers of 2, 2.5, and 3. So when you compare this streamlines of both this blunted wedge as well as blunted wedge, you can see that in case of blunted one, yeah, okay, what happens is this the blunting will basically reduce this vortices. So vortex form, okay, this recirculation zone is reduced with this blunting. So mixing is something affected. So here this is actually uh, diamond strut. Okay, diamond strut at different Mach numbers 2, 2.5, and 3. So in case of diamond strut, when compared to that of wedge strut, so strut, the recirculation zone is something reduced. So that means the flow fuel air mixture almost flows parallel to each other. So that means the recirculation zone is more in case of this, that vortex formation is more in case of this wedge strut and compared to that of diamond strut. So this is diamond strut with um, without blunting, and this is diamond strut with blunting. So we can see here when compared to wedge strut, the recirculation zones are less in case of this diamond strut. So because of this recirculation zones, the wedge strut provides effective mixing, so that mixing efficiency is higher in case of wedge strut and compared to that of diamond strut. So we can, if we compare this mass fraction of hydrogen for different strut configurations at 2, 2.5, and 3. This is for all the configurations: wedge, blunted wedge, diamond, and blunted diamond configurations. So we can see that so in the combustor length, we can see that the duration required for wedge strut is less when compared to that of other configurations. This is actually wedge strut, and this is uh, okay. So this is the time required for okay, this is so that means we can see that the wedge strut requires less combustion duration when compared to that of other configurations. So with increase in Mach number again, this duration is reduced, of course, but anyhow, the wedge strut requires less combustion duration when compared to other configurations. So that means diamond strut requires more combustor length for the effective mixing of the fuel and air. So wedge strut requires less duration. So these are the static temperature variations of wedge, okay, at different Mach numbers, and okay, inside the combustion chamber at different Mach numbers. And then so here these are the mixing efficiencies for comparison at of different configurations: diamond, wedge, blunted diamond, and the blunted wedge. So at different Mach numbers we compared. So the mixing efficiency is higher for wedge strut and compared to other configurations. And of course, the total pressure loss is also. So these are the mixing efficiency curves for okay, all configurations considered at different Mach numbers. But however, we observed very less variation in when with increase in Mach number with the mixing efficiencies. And the total pressure loss we can see here. The total pressure loss also is more for wedge strut. So that means when you compare the wedge as well as diamond struts for mixing efficiency and total pressure loss and the combustion duration. So the wedge strut requires less duration for complete mixing of the fuel and air. Uh, and of course, the mixing efficiency is more for wedge strut and compared to that because of this recirculation zones. So longer recirculation zones of the wedge strut provides effective mixing when compared to other configurations. So because of that, the combustion chamber length can be reduced in case of wedge strut. Okay, thank you. So thank you very much for your learning.
Sir,
Yes.
sir. Thank you very much, sir. Sir, dear participants, if you have any queries, please ask. Dear participants, if you have any queries, the resource person is here. You can ask, please. Any queries, dear participants? Okay, sir. Venkateswarlu, sir. Thank you very much, sir, for the valuable session.
Yeah.
Very informative, sir. Thank you very much, sir.
Yeah,
Thank you,
thank
sir.
you, sir.
Thank you, sir. Thank you, sir.
Thank you for
Thank you,
giving
sir.
this opportunity. I thank
Thank you very much,
organizers.
sir.
Yeah, I thank the organizers and the college, the principal sir, and participants for
Sir.
giving this opportunity to present this session. Thank you very
Thank you
much.
very much. Thank you very much, sir. Thank you, sir. Okay, sir.
Okay, right. Thank you.
Okay, sir. Thank you, sir. Okay, dear participants, we will wait for next resource person to arrive. Meanwhile, please take a break. Another resource person will attend in a short time. Please wait. Thank you. Sir, Venkateswarlu sir, please stop sharing, sir. Can you please stop sharing, sir? Thank you, sir. Okay, sir. Dear participants, next resource person will be joining in between 5 to 10 minutes. Thank you for waiting. Sir, Hari Ganesh, sir. Hari Ganesh, sir. Are you there, sir?
Yes, sir. This is Hari Ganesh. Actually, my mic was
Sir.
on mute. Now it is
Okay, sir. Good evening, sir. Good evening, sir. Thank you for joining, sir.
Yeah, good evening. Good evening, sir. How are you?
Fine, sir. Thank you, sir. Sir, first I will introduce you, sir. Then afterwards, you can share the screen and you can start, sir. Just I will introduce you, sir.
Yeah, sure.
Okay, sir. Okay, dear participants, the renowned resource person, Mr. Hari Ganesh Arangi, just now joined. And first, I will introduce the resource person now. Mr. Hari Ganesh Arangi possesses an impressive 29 years of hands-on industrial experience spanning both India and international markets, where he has worked with renowned organizations such as Tata, GMR Energy, Thermax Limited, Tokyo Denki, and several others. He now leads his own company naming Mahakrish Technical Services Private Limited company, delivering a diverse array of specialized services related to power plants. These services cater to clients across more than 10 countries, ensuring comprehensive support services like execution, technical consultancy, operation, and maintenance. Mr. Arangi holds an MTech degree with a focus on thermal engineering, and he is also actively pursuing a part-time PhD from NIT Silchar in Assam, advancing his expertise in this field. He maintains active memberships in key professional bodies including MIE, Institution of Engineers India, CE Chartered Engineer, and ISTE, Indian Society for Technical Education, reflecting his commitment to ongoing development and industrial standards. And sir, Mr. Hari Ganesh, sir, now I'm handing over the session to you, sir. You please share the screen and please start, sir.
Yeah. Good evening, all. It is a nice opportunity to have a interaction with the academic by sharing our industrial experience. Yeah. My screen is visible.
Yes, sir. Yes, sir. Visible, sir. Please carry on, sir. Sir, please carry on, sir.
Yeah. Now this topic is on optimizing energy efficiency in power plant operations. My background also since past about 29 years working in the power industries as addressed Mr. So we are undergoing like in this past decades, we have seen several changes in the power industries also. Few things just I will share today. Now, like everybody knows, like what is the power plant means? It is nothing but generation of electricity power, and where the electricity power is uh, getting from the several fuels. It is a fossil fuels and renewable energies. And basically, the power plants are operating with the steam turbines and gas turbines and hydro plants, where the steam turbine operates on the Rankine cycle, like that pump taking the water. It is a one to where the 1 to 2 is the isentropic pump process. It is like a pump is taking the water from the dehydrated tank. There is the water storage tank, which is a DM water. That pump is taking that low pressure water, and it is increasing the pressure up to like 90 bar and 250 bar, depends on the power plant uh, capacity. That high pressure water enters into the boiler where the heat exchanging takes place. That pressure will be the constant. There will be in the heat addition, that is the process 2 to 3, where that by burning the fuels, either coal or biomass fuel or gas, that high pressure water that converts into a steam, and that steam, high pressure steam enters into the steam turbine. That is where the steam turbine process is that high pressure and temperature both gets a drops, where the isentropic process takes place from 3 to 4. That in the turbine is having a several stages of blades, where the rotating blades and fixed blades. From there, that mechanical energy, where the heat energy converting into the mechanical energy is converting into the electrical energy, that where the electricity is generating through the steam generator, which is coupled to the turbine. Again, that low pressure steam, low pressure and condensate, partially it enters into the condenser. In the condenser, through help of the cooling water circulation, that low temperature steam, it gets a condensate, and again it pump into the deaerator tank. From deaerator, again it takes to the feed water pump. Then the same process. The reheating cycle, where the Rankine cycle, like a simple cycle, it operates like, whereas the low megawatt, low capacity power plants, where the reheat cycle, where it improves the efficiency of the turbine and power plant, where that like there will be a multi cylinders, either double cylinder or 3 cylinders will be there, like a HP turbine, IP turbine, and LP turbine. That first, when after the boiler steam enters into the HP turbine, from HP turbine, that steam again comes back to the boiler, where it takes a reheating. Again, that reheating high temperature steam enters into the IP. From IP again at the LP turbine. From LP turbine comes to the condenser. Again, the process remains same. Where in this reheating cycle we get the more efficiency. This is the combined cycle plant, where it operates like both with the gas and that either natural gas or LNG. Through that, it will enter, that gas will be filtered into the gas conditioning skid. From that skid, that around 25 bar pressure gas, it enters into the gas turbine. From gas turbine, before that, where the combustion zone is there, before that there will be a compressor. It is attached to the one skid only. That compressor takes the air from the atmosphere, where it intake air filter will be there. That fine air will be compressed and it will be burned in the combustion chamber, and that high pressure exhaust gas, it rotates the gas turbine. From there, that high temperature flue gas, it goes into the again heat exchanger, where we call as a HRS, the heat recovery steam generator. From there, it will go out to the atmosphere through chimney. In that again feed water is pumping from feed water pump to the boiler HRSG. From HRSG, the steam will go to the steam turbine, and steam turbine also will operate. So in the both combination, again we get a good heat rate and efficiency in the combined cycle plant. This is simple, like a coal power plant. This coal-fired power plant, where it is in this showing is the boiler, and ESP majorly it is visible with the field feeding coal conveying system. So for any power plant, like how to proceed, like okay, I want to establish one power plant. So what is the steps basically involves, like what is the path? Like first we have to decide what is the capacity of the plant we want to establish. So after establishing the like a capacity, we have to basically, there will be a 2 major drawings need to prepare, like a heat mass balance diagram and water balance diagram. So like from where we are taking the fuel, water, and how we are consuming, again that water balance diagram also, like that wastewater will be generated, and it is simply cannot be disposed to the atmosphere as per the present environmental conditions in our India or most of the European countries, Asian countries also, except the Africa. Africa having a vast area of the land. So, their people used to like unofficially they used to discard the water. So first we have to prepare both the HMBD, WBD, and then based on that, there will be detailed drawing will be prepared and statutory approvals also to be taken from the government body. That is environmental clearance and planning approval and like a boiler officer and chief electrical inspector of government take the approval. Then that specifically like what kind of the equipments are required, like how we decide this is the I need at my home is like some 46-inch TV. So then which company will go, like we will similarly for that equipments also there will be a technical specification will be floated. Based on that, there will be a qualified, we will select the qualified vendors who supplies the material. Then there will be our design and what they are giving. Both the designs will be matched with the design approval. After design approval, it will go to the under manufacturing, either boiler or turbine or remaining auxiliaries, whatever it is. During the manufacturing, inspection process will be there. Then after that, material will be supplied to the land where you have proposed and you have taken the approval. So there that execution will take place with respect to the civil, mechanical, electrical, and instrumentation. Then the total work, like execution work, will complete, and it will be even before just it won't run any equipment. First, it will be taken like a motors will be taken as a no load trials, like a without coupling, whether this installed motor and installed cables are everything okay or not. Those testings will be done. That is called like a pre-commissioning checks. And after that, there will be a cleaning process of the installed pipes or equipments. There will be a flushing procedure. In the gas plant means they used to do the calls as a pigging. That gas pipeline they used to clean with the pigging process. Even boiler used to clean with the alkali boil out, like this. Several processes, several equipment will be cleaned. Then it comes as a commissioning part. Commissioning part means continuous running of the equipments and giving the steam to the turbine. Then generate the power. That power generation, some places they use for their own purpose, small plants, like cement plants, sponge iron plants, and other IPPs and all, they will export. And even small plants also, if they have an agreement with the government, they will supply the power to the government also, that grid. This is why the plant layout is required and all. Because to optimize, like to fix what is the area required and how we are going, that is the main purpose of the plant layout. This is the typical one of the plant layout. It is in gas, like a combined cycle power plants. Then what we have discussed, like a HMB heat mass balance diagram. This is the typical, like how much megawatt we are going to generate. Previous one is, this is for the steam turbine plant, coal plant, and this is the combined cycle plant. This heat mass balance diagram, where at the bottom, this bottom left, here it is a gas turbine area, and this tall, whatever the rectangular you are looking, this is the HRG, heat recovery steam generator. From there, steam will go, and right side, this path is the steam turbine area. Right bottom. This is the typical water balance diagram. How we take the raw water and what we do the treatment before taking to the boiler. This is the typical process and instrumentation diagram. Like what are the pipings equipments are there to control like a operation? What are the instruments we need to provide? This diagram indicates. And this is a single line diagram with respect to the instrumentation. We have discussed like earlier diagrams and mechanically discussed. Then whatever the electrical also, this is the diagram how to prepare, so that like how we are taking initially power and how we are distributing the this auxiliary power, and after generating how it will be exported. It's a typical like a thermal power plant equipments. This picture indicates that like approximately 25 megawatt boiler, vertical boiler, and this is a 660 megawatt power plant boiler, where the ID fans and chimney and the blue color, what are the sheds you are looking, these are the ESP, electrostatic precipitator. And as the boiler has to require the some airflow at a different levels. So these are the ID fan, FD fan, induced draft fan, and forced draft, primary air, secondary air fans. As well as this is the prime requirement in the any power plant, or if nowadays if you see any cinema hall, like any complex, anything, firefighting systems, which is a crucial in the any place. So these are the typical firefighting system. This is a steam turbine area, like this green color is a turbine, middle gearbox and generator. That is lower megawatt. This is the 800 megawatt, where we have discussed like a multi-cylinder. If you take from left to right, that first one will be the HP cylinder, then HIP, then two LPs, like a LP1, LP2, then generator. This is a combined cycle gas plant. This is the gas turbines, where the in the gas turbine area also like a gas turbine and connected with the generator, one setup. In the same plant, steam turbine will be connected to the another generator, like it is called like a multi-shaft or dual shaft. Whereas this plant is, this is from Singapore, this is like a single shaft. There will be a generator in the middle. One side will be the gas turbine will be connected, and other side steam turbine will be connected. When the steam is not there, only gas turbine and the generator only will be operated, and power generation will be around 240 to 250 megawatt. After the steam generation, the steam turbine gets coupled automatically with respect to the triple S clutch. Then the steam turbine also rotates, and that also gives the power, add-on power. So it is a capacity of the 385 megawatt unit. When the gas turbine opens, it looks like this, the different stages. Compressor, this initial area up to this part is a compressor area. You can observe the difference in the blades structure. Last stage, that three stages are different, and front stages are different. Front stage is the compressor area, and the last stage is the turbine area. Typical condenser. In the condenser also, most of the plants where the water scarcity is there, in that case, people use the air-cooled condenser also, where we don't require any water to cool the that low temperature steam and get the water. So this is the air-cooled condenser. Earlier, what we have seen, this is this water-cooled condenser. There will be a cooling tower. In that cooling tower, water comes to this condenser. So equipment also increases. This is the feed pump boiler, feed water pump, where the water pumping to the boiler. There will be a feed water heaters to increase the more efficiency respective of that water before sending to the boiler. After the boiler feed pump, it will be passed through a on heat exchanger, where that steam will be taken from the turbine. That steam will heat this feed water, and it will pump to the boiler economizer. So there will be a, when the temperature like a 10-degree high temperature water goes to the boiler, then you are saving again a fuel combustion, like a quantity of the fuel you will save. So this is the to increase the efficiency. Typical cooling water pumps, wherever the surface condenser is there, like a cooling tower and cooling water pumps will be used. That is the IDC, induced draft fans, and these are the natural draft cooling towers. this efficiency, how to increase the each equipment efficiency also in the next slides we will see. Where the typical pipings and all what we use in the power plants, walls, pipings. That instrumentation also with respect to the instrumentation, we use the like a pressure monitoring system, temperature monitoring system, flow measurement. That will be analog or digital will be there. These are the few of the instruments to check the first one is the pressure transmitter. Even this pressure transmitter is not only for the monitoring, and it will control the several valves and like for the tripping system also. So this is one kind of a control systems. And middle one is temperature elements. When it raises high temperature, that equipment will get tripped to avoid the major damages. And third one is vibration probes, where it gives the like a equipment, it has to operate smoothly. If it is any abnormality, any high vibration, it will indicate and it will trip the machine to safeguard. This is the another vibration monitoring system. This is also vibration monitoring system and analyzer also. Analyzer means this machine gives indications. It will like when any problem, like exactly we don't know from where the vibration is occurring. Then we use this analyzer to inspect. It will show that the exact source of the vibration. These are the switchyard after the power generation where it is pumping to the grid. This is a typical control room. And to build up or operate any power plant, couple of the standards are involved. As per the standard, like I cannot build or I cannot operate with my own. So some international standards we have to follow, Indian and international standards. Those are ASME, ANSI, ASTM, API, IS, CA standards we have to follow. Now coming to the point, like about the optimization and efficiency respect to increasing. Like this is the balancing the energy trilemma. That means reliability, efficiency, and ESG. These three respective we have to operate the power plant to improve its efficiency and optimize. Like reliability ensures the uninterrupted supply via grid cores and redundancy, such as some places like DG sites, robust earthing design, we have to make it up. And PLC DCS are used to control and monitor operation of the plant. And about the modernization, what is the key objectives for any plant, like a modernization, upgradation, what are the main key objectives are involved, like a one is the assessment, like regularly we have to do the audit, because when the plant is regularly operating, there will be some erosion will be there, or erosion, corrosion, or utilization respective, like a weakness also will be there. So with respect to that, like assessment, regularly there should be some audit reports will be there. There should be auditing will be done, and upgradation also. Like systems are like continuously it is upgrading. Either like initially it was using a like analog system, then later it will be digital. The digital also initially again like a PLC system SCADA were using. Then it is DCS system came into the picture. And now that from DCS it is like a remote monitoring also. Even plants are operating in India, where the US people like a GE and all Siemens, they are monitoring our plants from here by sitting in the US or Italy, and they are just guiding like if there is any problem, anything, just they are guiding how to do it. And those implement like a suggestions and all we have to implement, and again monitoring system. With this improves a PLF by 5 to 10%, and outages will be reduced, and it will be aligned with the ESG, means that environmental safety and governance law with respect to this also it will be in line. Now next coming to the boiler efficiency factors, mainly affects as a combustion efficiency losses. This combustion efficiency when the fuel combustion efficiency losses in boiler occurs when fuel energy fails to fully convert to heat due to the incomplete burning, typically accounting for 2 to 5% of total loss in a power plant. So that fuel improper burning, that improper air flow, and any in the fuel also if there is any moisture, that fuel will not burn properly. So that also will be a losses for the plant. Then mitigation measures, optimizing burners for staged combustion, using the PLC DCS control system for interlocking and logic systems like a real-time O2 monitoring and maintain regular audits, and retrofitting low NOx burners and air preheaters can recover 1 to 2% efficiency, supporting to net zero goals. These are the typical that burning system where the furnace it is a or a boiler furnace area, like just some time when the fuel have dumped as a lump and it is not properly burning, just they are opening the manual door and adjusting the fuel with the, you can see the with the long piping or rods. And next loss is the radiation and convection losses. Radiation and convection losses in boiler represents heat escaping through the furnace walls, reducing overall thermal efficiency by 1 to 3% in power plants. Mitigations, regularly auditing and FRLS materials using and retrofits like a ceramic fiber blankets to cut losses by 50%, aligning with the net zero efficiency goals. This is towards the modernization of plants. You can see this, how the radiation affect because of the improper insulation or inside the boiler. You can see that outside insulation cover, that insulation cladding sheet, how the color has changed. You can see like it became a pink and a reddish color. This is because of improper insulation, and this is a very much huge loss to the boiler efficiency losses. And next is a dry flue gas loss analysis. This dry flue gases losses means like again improper injection of the air, so that this improper combustion will take place. So that flue gases also, it will not exchange the proper heat to the, when we are taking any air inside that coal, even that fuel also we will heat it. That heat exchange will not take place properly. So you can see like from chimneys how that flue gases are coming like in the color. Normally, in a good operating power plants, you will not see any smoke. But in these pictures, hope you can see the smoke. It is ejecting from the chimneys. Next efficiency way is VFD applications in the ID, FD, and cooling water, cooling towers and cooling water pumps, PFS. This is because initially we no need of like a fans to rotate in its rated design speed, because initially it requires only less speed as the initial load will be very low. So that time by operating like a full speed of the motor, unnecessarily you are wasting the energy. So by installing the variable frequency drives, we will optimize the power also. This is the example of the VFD. The left side are the VFD panels, and inside this kind of a component will be the right side. Sorry?
Sir,
Yeah.
you please carry on, sir.
Yeah,
Yes.
left side is the VFD panels, and the right side you can notice the VFD inside that panel, that drives. These are the drives components. This how the energy destruction breakdowns in the boiler 80 to 85, and the turbine 5 to 10, and the condenser is the less than 2%. Next comes the air preheater. Air preheater where that performance is depending upon the that air preheater, say the tubes leakage or seal leakages, because that air we are using for the combustion of the fuel, where like if the APH leakages in air preheater allows the hot flue gases to bypass heat transfer or mix with the cold air, increasing the ID fan power by 5 to 15%. So that ID fan loading is increasing and rising existing gas temperature 10 to 30 degree, which amplifies dry flue gas losses. This can be avoided with the seal tightness or tubes, proper welding. So for this, like every time there will be a preventive maintenance is required to check this any tightnesses. That is once in a year, 20 days, 25 days, like a plant has to shut down and check all these leakages and pressure tests. Then better to go for the again next running. And these losses we can observe in our DCS system or PLC connected system in that where we can see, okay, that computer like what we have shown the DCS system, there we can observe different, like it will vary that this air preheater, when the air temperature is low, obviously it will affect in this fuel heating area. The temperature it will show that so improper hot air is coming. Next comes a soot blowing. Soot blowing is used to clean these boiler tubes where it is when the fuel is burning, there will be ash. That flue gas ash will be accumulated on the tubes at several places inside the furnace area, superheater zone, economizer, APH area. So this ash regular intervals, it should be cleaned with the soot blowing process. So even this soot blowing process, if it is properly operating, improving the boiler efficiency by 1 to 3% and cutting steam use by 30 to 50%. So that much effect it gives the soot blowing. Using this AI to determine fouling levels, that AI driven soot blowing optimizes the fouling detection in a boiler by analyzing real-time data from sensors, cameras, or flue gas analytics to trigger cleaning only when needed, reducing the energy waste by 1 to 2%. Normally, the soot blowing, what we do in the industry practice, every 4 hours, 8 hours, it used to operate. If this AI driven, like there will be some camera monitored and how much ash is accumulated. If there is no ash is accumulated, even no need to do the soot blowing. When you are doing a soot blowing, there will be a consumption of steam and there will be a motor also. So power also will be consumed. So these two things also can be saved if it is a properly AI driven like monitoring if it is there. That soot blowing, this is an example of like a rotary soot blowing. And this is the long retractable soot blowing. There will be like a lancer will be there. When it operates, that will go inside the boiler and cleans. Fouling detection also. AI models process parameters like a air preheater, differential pressure, gas temperature, O2 levels, and infrared images to predict a soot buildup levels, outperforming fixed schedules. Machine learning correlates fouling with the combustion efficiency drops or ID fan power spikes. This will because the soot blowing, if you are improperly doing, if it is not doing also, that ash will accumulate on the heat boiler tubes, that water tubes, and there will be a improper heat exchange, and you will not get the proper steam also, and boiler efficiency will be down. You need to burn the more fuel. Predictive soot blowings and using algorithms to forecast fouling rates based on coal quality, load variations, and historical data. Because all the coal are not same. Where mostly in Indian coals we have a higher percentage of the ash quantity, whereas the like Indonesia or South Africa coals having the ash quantity less and calorific value also more. If it is the ash percentage more in the basic coal itself, that ash will accumulate in this boiler also. So benefits of this: cuts dry flue gas losses by maintaining the APH efficiency, extends cleaning intervals by 20 to 30%. As I told, like that cleaning intervals, it can be increased. Instead of 4 hours, it can be done by 8 hours. And supposed to net zero via lower emissions integrated with VFD fan control during CM mandated audits. This is a typical like air preheater, where one side air will be there and this ducting side flue gas will be there. Next is this where we have discussed that the boiler part. Next comes is the turbine area also. The turbine is efficiency is monitored or calculated with respect to the heat rate. That heat rate, it impacts with the deviation in the main streamline pressure and temperature, and the reheating steam parameters and the heat rate degradation. With these parameters we are monitoring through this PLC connector or DCS connected monitors, and from here only we will operate the whole plant also. All are connected with the programmable logics in the software, and it will be monitored in these systems and controlled. These are the desk operators, what we call. With this turbine efficiency affecting on the that isentropic efficiency of HP, IP, and LP turbines, steam path audits, and blade degradation. Several times this due to the low temperature of the steam, it degrades the inside the turbine blades. Even the turbine blades gets eroded. It will be like a rat biting, or if the improper water parameters, where the phosphate, silica, if it is more, and again that it will coated on the turbine blades, again you will get the, like when the coating is more on the turbine blades, to drive that again you need you need a more energy, like a more steam. Again it is a losses. And steam path artist and blade degradation, gland steam system, and vacuum tightness. That is the way to tighten the like a vacuum. We have to take into the turbine, and that vacuum also up to such a 60-70% through the ejector or vacuum pumps will take. Rest if it has to go to 100% vacuum tightness, we have to give the gland steam system. That will be low temperature. Steam will be supplied to the turbine. There will be both side glands will be there of casings. When the outside at the edges there will be a glands, what we call as a labyrinth fins. In those areas we have to give the sealing steam, so that vacuum losses will not be there. Because even like a 1 kPa of the vacuum increases, there will be a improvement of 1.5% in the heat rate of the turbine. Next, coming to the condenser, it is a cooling water inlet temperature also it affects. As per the design, it should be maintained. If it is like a 32-degree temperature, inlet temperature, if it has shown, if it is indicated as per design, if we are supplying the 34 or 36, again that performance comes down. Air ingress detection, that air ingress, like sometimes if the air anywhere from welding leaks or any welding joint failures, if the air ingresses, again that vacuum reduces and that efficiency will come down. Feed water chemistry, which plays the major role in the any power plant. It is like a one kind of a heart only, because if you maintain the water quality in a proper way as per the standard design conditions, like that turbines and boilers, where the major equipments are in touch with this water, so it will be no need to do the for a maintenance in a long time also. If the water quality is bad, there will be scale formation, there will be puncture, several ways it will be there. Like example, water parameters monitoring, pH, conductivity, and dissolved oxygens. This is one of the sample report, like how the water quality will be monitored in any plant. If you take like a DM storage tank, pH and conductivity, TDS, hardness, and silica, and hydrogen alkalinity, phosphate, how they are monitoring DM storage tank where it is generated, then feed water, condensate system, steam, like a boil, all the several places they will monitor, they will test it, and regularly they will like once in a 4 hours, once in a 8 hours, they will regularly check this water quality. If there is any variation, they have to improve by dosing some chemicals. They have to improve the water quality. Sealing steam system, what we have discussed. This auxiliary power in normally any thumb rule, approximately around 5 to 10% is 5 to 10% of the total capacity of the plant, that auxiliary consumption will be there. That 5 to 10% auxiliary consumptions also effectively we can minimize by using like what we discussed, VFD drives. VFD drives normally it will be used at where the high impacted areas, boiler feed pumps, IDFD fans, and cooling water pumps, even cooling tower fans also. Yeah, this VFD drives and soft starter benefits also. If we use soft starters also, we can control the power consumption. Yeah, pump impeller trimmings. Like after some intervals of usage, there will be a erosion will be there, so that impellers regularly will be checked, and it will be modified or it will be retrofitted. And more by using the high efficiency motors like a IE4, IE5. Normally earlier it used to be run like a IE2, IE3, but gradually it is replaced with IE4, IE5. So it is a high efficiency motors where the losses will be less. And other lighting area, instead of a normal lamps and all, LED bulbs and a smart lighting system like a control system with respect to the like a daylight, like when the sunset is coming, that time only lamps will glow, or with the walking sensors, such a area where it is not required by walking sensor systems, that time only that lights will glow. Because of this, there will be a power saving in the generation also. So obviously we are increasing the efficiency for that plant. Cooling tower optimization, fan cycling strategy based on ambient wet bulb temperature, and we use this variable speed control systems. And cooling tower where it is having a fills, that fills will be better to check and replace every 2 years, 3 years, 5 years, because that is the raw water will be used in the fields. Sometimes it will be a biofouling will be there, coatings will be there, or it will be come to a brittle condition, so that regular intervals of the cleaning and replacement is mandatory to improve the plant efficiency. Yeah, like another improvement process is by using the ultra supercritical boilers. It is a high pressure boilers where there will not be any like a directly water gets into the like a steam. There won't be any steam drum or steam separation will not be there. It is called as a once through boiler technology. And there will be like a real-time by real-time performance monitoring and using the AI for suit blowing systems and predicting the boiler tube leakages using acoustics sensors. Like a boiler tube leakages when it is running, until unless like a experienced or some more leakages, people will not come to know whether it is a leaking or not. So this kind of like a acoustic sensors, it will give that difference in the noise when the water leaks. By the sensors also we can minimize the major failures in the boiler. This condensate water systems recovery also, like a way the drain systems will be there. Normally, sometimes the drains they used to throw into the atmosphere or out of the steam zone area. So without wasting that steam, it can be recovered through a flash systems will be there, like a drain water, atmospheric flash tanks will be there. Through that water can be recovered. And heating integration also, utilizing turbine extraction steams, supplying the thermal energy to local grids, revenue diversifications, and digitalization. These are some plants used to be under analog system. If you see the picture, it is a totally analog operating, analog based operating the power plant. This is one of the other country. So totally, if you see all are there, you cannot see any digital. All will be like an analog system only. By replacing this digital system, it is a saving of the total money and increasing the efficiency also. Where that manual system like an analog system is replaced by using the proper instrumentation system and integrated with this DCS. You can see if you observe right side, two monitors, it is showing bottom one is the turbine area and top one is the boiler area. That monitor indicating. A for the performance monitoring, real-time heat rate tracking models, deviation analysis, signal design data, automated reporting systems, and any if there is any alarm, any abnormality in the operation of any equipment, it will give the alarm indication either it will make the sound like alarm, and that operator can take the properly action. So by DCS and AI system, we can make a unsupervised learning algorithms, identifying the drifts in equipment behavior, early warning systems, and machine learning for combustion system, dynamic optimization of a fuel air mixer, neural networks for boiler control, reducing the NOx while maintaining the efficiency, and data visualization by implementing the HMI based designs with the principles of the UX, high impact operating dashboards, situational awareness improvements. This human element by changing the management strategies and upskilling the staff for data interpretation and fostering a culture of innovation. By regularly, by training the existing team, even by brainstorming, it can be optimized in any plant, either power plant or any operational plant. This is the one of the sample of the training of the in-house operators and engineers. And the maintenance respective also, like a predictive and preventive maintenance. And with that preventive maintenance planning, we can minimize any breakdowns. Still there may be that unforeseen breakdowns will be there, but majority 99%, 95% will be minimized. That in the vibration analysis system also, one of the a preventive system, by detecting if there is any unbalanced misalignment and any bearing faults. This picture is showing that he is analyzing from where the vibration is occurring. So by spectrum analysis and all, it will be done. By connecting the right side, you can see that multiple probes have connected to the vibration monitoring system. Next is spare parts optimization. Using the proper data like a budgeting and proper planning, we can use that reliable data to size inventory. If there is any damages that taking place, if you are going that time to purchase any bearing, so total that downtime is a loss for that plant only. So loss means it is a money loss. If it is equipment is not running, then it is a purely money loss. So for to avoid that, we can maintain the spares inventory data, what are the critical spares, what are the non-critical spares, So majorly critical spares used to be maintained by any plants. So those will be reducing the carrying cost and just-in-time procurement and strategies. And when anytime, like it is a human psychology, when the other person come to know you require that item immediately, there may be a chance of he will increase the price. Like if you have a time for that same bearing or same gasket or same seals, you will ask for 2, 3 vendors, whoever gives the for less price, you will purchase. So you will be saving the money also in that respect to initially, and in future also downtime of the equipment also you are reducing. And NOx and SOx reducing technologies, that is a selective catalytic reduction basis and FGD basis. Nowadays, many plants are implementing these FGD flue gas desulfurization systems. It is a government has made a mandatory for the majority of the plants which are above 100 megawatts. ESG reports, that is the environmental and safety and governance respective. The data collection, sustainable reporting framework, transparency with the stakeholders. Yeah, these are the some kind of a we have discussed about the optimization and improving efficiency, improving methods in a power plant. Thank you very much for the opportunity given.
Sir, thank you very much, sir, for the valuable session, sir. Dear participants, now it's time for queries. If you have any queries, please ask.
Good evening, sir.
Yeah, good evening.
Sir, I'm not from technical background, but still I write down some keyword from your presentation, and
Yes, ma'am.
I want to ask some technical word. Like what word I know I want to say first. Like change management. It's about human element. As I'm the faculty of management and upskilling, innovation, culture. Actually, I want to know about some keywords that is like you said turbine, right? So can you tell me a little about turbine, as we have some topic in our UGC net paper, like we are when we are making electricity, any kind of electricity, hydro, tidal, geothermal, wind,
Yeah.
solar, any kind of energy. So we use turbine word. Can you please
Yeah.
explain in very simple way?
Sure. Just few minutes. Just I want to take out some picture, and that picture just I would like to explain.
Okay, sir. Okay.
Ma'am, are you from Haryana?
Yes, sir. Yes, I'm from Haryana,
From
from
which
Kushetra.
district? I am
From
from
Kushetra.
Bhiwani. I am from Bhiwani, ma'am. I am basically from electrical domain. And sir will
Okay,
tell
sir.
you everything about turbine, but really you asked a good question because in management, these type of the
Actually, yes, sir. Actually, when I was preparing for my net, I also give some tuition for net also. But we have like this energy. We need to use turbine. So I just want to know, because these are
Yeah.
exactly,
very technical word for
exactly,
us.
exactly.
Yeah.
Sir will tell you in detail, ma'am.
Yeah.
My screen is visible. One turbine photo.
Obviously, sir, screen is visible,
Yes,
sir.
sir. Yes, sir.
Yeah. So,
Yes, sir.
man, if you take like my cursor, just I'm moving the cursor. This is the like a where the steam pipeline it is entering into the total. This zone is it called as the steam turbine area. This up to this yellow part. Whether my cursor is visible, what I'm marking.
Yes, sir. Yes, sir. Visible.
Yeah. Yeah. So up to this yellow part, before this blue, in the long distance, we can see motor. Before this area, up to this area is steam turbine area. From this is the instrument where temperature pressure gauge is installed. From this front point to the up to this is a steam turbine area. Here I will explain you. from this piping where the insulation is there, from this steam piping, it enters into the first, there will be a chest will be there. The chest means control walls. What we study in our books, governor. Like here in this chamber, it is insulated. It will be made with the chromium molybdenum base, that casing, and that casing is because of the temperature in the steam, it should be insulated. This insulated inside the pot, there will be inside like a 3 walls, 4 walls will be there. That wall will operate how we studied in the governor, like a with respect to the load we are taking. One by one, that wall will inside will operate, and it will allow that wall opening, and that steam will enter inside this steam turbine. Yeah, now I'm showing the, first we have seen right hand side, this is the left hand side. This insulation, top is insulation, and this area is a totally turbine casing area. It will enter, so that the heat energy, that steam with the high temperature heat energy, it is rotating this steam inside the rotor blades. So it is converting into the mechanical, where in this mechanical energy, this blue color, actually in this photo, next photo, I think in our presentation, one photo is there. Yeah, here in this green color, first green color, that steam enters in this turbine and rotates. This is the low temperature where it gets the low temperature after expansion. And this middle is, this will be turbine speed will be at around 6,000, 7,000 for the low capacity, whereas the high capacity means it will be a 3,000 RPM. And the middle there, it's shown is the gearbox. Sorry. Middle green color is the gearbox. That mechanical energy, heat energy converted into the mechanical energy. Mechanical energy by rotating this. This is the generator, madam. This white color you are looking now. This is the generator.
Yes, sir.
So,
Yes, sir.
yeah. So that mechanical energy generator, where it is that a rotor is a rotating, it will be speed will be around 1500 RPM. So in this speed, when it is rotating, due to that EMF effect, we are getting the power, and mechanical energy is converting into the electrical energy in this chamber, in this area, in this alternator or generator, what we call.
Thank you, sir.
And in this picture also, this is the generator, what we call as a. So after the steam gets expansion, and that low pressure steam with the 45-degree around temperature, it will goes to the down, and in the condenser process, it gets the cooling down. So that you are aware about the condenser area. Actually, in this not only mechanical, in a plant like this is the instrumentation part, where the EC department is involved in these instruments, like what I am showing. These are the transmitters and controls. Here, instrumentation and EC departments involves. And anyhow, there will be a panels, breakers, and transformers, where it will be like a electrical department is involved. I can show you some kind of a panels, how it goes erection.
Sir, in this, sir, electrical department is also involved in this. As you are saying, EC department. In the same department, electrical engineers are also working.
Okay, if you see, these are the panels, kind of VFD panels, and these panels. If this is execution stage, one of our project is going on. Yeah, like this panels. If anybody is interested, like even they can visit for their academic interest. So even we have a chance and opportunity Like in the few, 2 people, 3 people, or 5 people comes, like a 2-3 days if they spend, they can gain the some practical knowledge, and it is easy to explain or helpful in the teaching of the academic area. This is an education stage. Like a cable connecting, they are connecting the cables and all. Yeah. So, okay, madam, next.
Any queries, dear participants, please ask. Sir, one question from my side, sir.
Yes, sir.
Sir, you said about digital twins, no, sir? Digital twins.
Digital?
Digital twins, you said, no, sir? Digital twins.
Digitalization?
Digital twins, sir. Digital twins. Digital twins, sir. TWINS, twins, sir. Sir, am I audible, sir?
Yeah, you're audible. Digital twins.
Yes, sir.
Maybe I don't think so, such a word.
Actually, in last slides, yes, sir, that one, sir.
The digital twin applications.
Actually, yes, sir, yes, sir. Actually, I heard that it is very costly like that. How can we implement this, sir, in digital twin? Actually, I'm doing PhD in CNC field, sir. CNC machines field. Yes, sir, yes,
Okay.
sir. Actually, I'm manufacturing one portable CNC, sir. Can I apply this digital twin technology to my CNC machine, sir? How can I apply any idea, sir, using AI like that?
Like frankly speaking, AI.
Sir.
Yeah, AI utilization in our industry, it is not not even fully, I can say. It is not at implementation is not at taken.
Okay, okay, sir.
Yeah.
Okay, okay, sir. Sir, one question in the chat box, sir.
Sorry, I didn't see.
For a simple Rankine cycle or Brayton cycle, irreversibility analysis is a proven way for optimization. Do you think irreversibility distribution analysis can be used for optimizing the combined cycle? If yes, how should one proceed for it? That is the question, sir. Is it visible, sir? In chat box, one question is there. No?
Yeah. Some Mr.
Yes,
Ashish Mishra.
Ashish Mishra. Yes, sir. Yes, sir.
For a simple Rankine cycle or Brayton cycle irreversibility analysis is a proven way for optimization. Do you think irreversibility distribution analysis can be used for optimizing combined cycle? This I will check it up.
Okay, sir. Okay, sir.
Yeah,
Sure, sir.
yeah.
Okay, dear participants, any queries? Okay, sir. Thank you very much, sir, for your valuable session, sir. It's very knowledge sharing, and you have shared your vast experience, sir. Thank you very much for your nice presentation, sir.
Thank you, sir.
Thank you, sir. Thank you very much, sir.
Yeah, thank you all. Thank you very
sir.
much. Bye.
Thank you, sir. Okay, sir. Good night, sir.
Good night. Have a nice time. Bye.
Thank you, sir. Okay, dear participants, actually, I have posted the feedback, but unfortunately, so many are asking that it is asking for access. we will check the feedback link and we will post it, or we will rectify that problem and we will post it again. And thank you for your valuable patience, dear participants. And I hope you
Ashwani
are
sir,
all. Sir, yes, please, sir.
actually, sir, this feedback link is asking for the permission, and
Yes, sir. Yes, sir.
you are requested to make and generate a new link and drop it in the WhatsApp group. It will be better, I think.
If possible, actually, that editing access must be given by the admin, sir. If it is given, you can get the access, sir. We'll
Okay,
rectify
okay,
it
Ashwani sir.
and I will let you know, sir, in the group, sir. In the
But
WhatsApp
sir,
group, we'll let you know, sir.
literally you are doing wonderful work, sir.
Oh, thank you.
For
Thank you
whole
very much,
session.
sir. Thank you very much, sir. It's my responsibility, sir. Thank you, sir. Okay, thank you very much, dear participants. And tomorrow is the last day of this FDP, and we will meet again tomorrow at 6 p.m. Thank you very much, dear participants. Now, and you can leave, dear
I
participants.
think
Sir.
tomorrow, sir,
Sir,
tomorrow I think it will be from 2 p.m.
Yes,
I
sir.
think
Yes.
tomorrow
2
is a
p.m.
Saturday.
Yes, sir.
You
Yes,
kindly
sir.
verify the schedule, sir, not 6 p.m.
Sir.
Tomorrow,
Okay, we'll
Saturday,
let.
last day.
Yes, sir. Last day, sir.
I think the schedule is start at 2 p.m.
2 p.m. 2
We'll
p.m.
let
sir.
you know, sir. We'll let you know, sir. Sure,
As
sir.
I saw the brochure,
Okay, sir. We'll let you know, sir.
the 3 sessions are there.
Okay, sir.
Okay, sir.
We'll let
Fine.
you
Thank
know
you.
the. Okay, sir. Thank you, sir. Thank you very
Okay.
much, dear participants. Okay, you can
Sir,
leave.
good evening, sir.
Participants.
When will be the
Yes, sir.
quizzes, sir? When exam, sir?
Yes, sir. We will let you know, sir. We'll let you know, sir. We'll talk
Yes.
with the convener, sir, and we'll let you know, sir.
Yes, sir. Okay, sir.
Okay, sir. Everything we'll communicate in the group, sir. WhatsApp group we'll communicate, sir. Okay, sir. Thank you very much, everyone.
Thank you, sir. Thank you.
Okay, sir. You can leave, sir. Thank you.